Okay, just quick review it here. What we're doing in the previous lecture, we're using Laplace transform to solve ordinary differential equation. And the process of solving ODE using Laplace transform involves a major process is this. First step, you're transforming the original ordinary differential equation from time domain, okay, this is t domain, into a S domain. So you get a S function for the output y of s. From y of s, and this major step is this: how can we decompose this y of s into the simplest form so that we can use the table to find its inverse Laplace? So this step here, how can we decompose into the simplest format, is what we have studied in the previous lecture. And I showed you two different approaches. Okay, the first approach, the first case is when and this y of s will be in the fraction format, so it'll be numerator divided by its denominator. Okay. So the first case is when y of s has distinct simple poles. So basically, when you set d of s equal to 0, and you get the so-called poles. When y of s has distinct simple poles, then you have a very simple way to partial fraction expansion, okay, to get the simplest format. The second one is the one that we didn't quite finish. So the second one is when y of s has complex conjugate poles. Okay. We did an example here. So when you're, let's say, if your second order ODE is this, and initial conditions are all 0. Okay. So in this case, so I'm going to skip a few steps because we did that in the previous lecture. So your y of s you get is 20 over s plus 3 s squared plus 8s plus 25. Okay, so you get y of s equal to this. So over here now we do the partial fraction expansion. Okay. So how do we expand this? You have a pole at here s equal to -3. So that's a simple pole. If you let s plus 8s plus 25 equal to 0, okay, and you'll find out its solution is a complex conjugate poles. Okay, so it's a pair of complex conjugate solution, and that basically falls into this case. If that's the case, we're not going to do anything at all to this. We'll leave it as it is. Okay. So the partial fraction expansion here will be a over s plus 3, and then bs plus c over s squared plus 8s plus 25. Okay. So this is how you treat the term s squared plus 8s plus 25. The numerator here is not just a simple constant. It has to be a one order short. So bs plus c. Okay. A, B, C are the constant that we need to find out. Okay. So how do I find A, B, C? We can use comparing coefficients. So basically you write it back into one piece again. I think I've done this in the last lecture. So you write it back into one piece again and group all the similar terms for the numerator, okay? And then compare coefficients with your original coefficient for the numerator, which is 20. Okay, so basically this whole term at here, it should be 20. Okay, so you compare coefficients, then you will get s squared term. There's no s squared term. You get a plus b equal to 0, and 8a plus 3b plus c equal to 0. 25a, this is s to the power of 0. 25a plus 3c equal to 20, the constant term. From here, you solve for a, b, c. So a equal to 2, b equal to negative 2, and c equal to negative 10. Okay. All right. So I think that's pretty much what we have end up with in the previous lecture. Okay. So now what do we have? Your y of s equal to 2 over s plus 3. That's a over s plus 3. And bs plus c over this. So this is b, this is a c. So let's put a negative in the front at here. So negative minus 2s plus 10 over s squared plus 8s plus 25. Okay, this is your y of s. With the partial fraction expansion, you get this up to this stage. And if we are going to take the inverse Laplace transform, this term is pretty straightforward, and that's basically 2 times e to the power negative 3 e to the power negative 3t, right? So it's this guy here. We need a little bit of attention in here. Okay, how do I get the inverse Laplace for that particular term? We make use of the table, right? Okay. The closest bet you get is these two. So if you look at these two here, right? Look at the denominator for these two. What's the denominator for these two? It's s plus a squared plus omega squared. Okay, this is the denominator. And if I let this denominator to be 0, let me see what's the solution here. So we get s plus a squared equal to negative omega squared. Then what's the solution for s? It's what? Negative a plus minus j omega, right? J omega. So it's a complex number, right? So this is exactly what we are dealing with here. The pose for the denominator is a complex conjugate numbers, and same as what's in this table at here. So that's what we're going to do. We're trying to match what we have at here with what we have in this table. So all I'm going to do is I'm not going to change this. Okay, so this is still going to be the same as its expression, but I'm going to manipulate this to write it in the same format as these two. Okay, that's what I'm going to do. Okay. So let's see what do we do with this guy here. Okay. So I'll single this out. I'll single this term out. 2s plus 10 over s squared plus 8s plus 25. Okay. So remember what we want to do, huh? We want to rewrite this one into this format. If you look at the bottom here, what's the bottom? S plus a squared plus omega squared. Okay. So let me write it down here. S plus a squared plus omega squared, which is same as s squared plus 2as plus a squared plus omega squared. right? Okay. So here's the bottom here. S squared plus 8s plus 25. So if I want to write into this formula here, what do I need to do? This 8 at here is what? Is a 2a, right? It's 2a here. So the small a is equal to 4. So that's 2 times 4 and s plus a squared, which is what should that be? 16, right? 16. But this is 25. So what do I need to add here? 9. Is that clear? So then the bottom here, right? So let's leave the top as it is first. And now the bottom here becomes s plus, I'll write this as a 4 squared. S plus 4 square, and then plus 9, and 9 is what square? 3 squared. So the bottom now is rewritten into exactly this format here, right? Yeah. Now don't panic if this number, for example, it's not 9. Let's say this number is 7. So what do I write here? I'll write, instead of a square root bracket 7, right? So you can always write it into something power. Okay. Okay, so that's this one here. So I'm done with the bottom, right? So now the bottom match to this now. Then I'm going to manipulate the top to match this and that. All right? Yeah. So if I want to find the inverse, if I can write this and then I inverse this, you can write this and then inverse this. So let's rewrite the top into exactly the format. So how can I write the top here? See the top, this is s plus a, and this is also what? S plus a here, right? It's also s plus a. So I want to write the top into s plus a. S plus a is s plus 4. Okay. I want to write this one into this. But I have a 2 at here, right? That's fine. I'll keep the 2 here. But I'm not going to change, but I will change the s to s plus 4. Okay. But I cannot change this question. This is 2s plus 10 originally. So now if I put a 4 here, that's 2s plus 8. So the 10 becomes 2, right? And 2. Now 2 might not be what we want at here. So let me see. I will further manipulate. And now I'm going to rewrite this. Put this into 2 fractions. Right? There are 2 fractions here. The first fraction is 2 times s plus 4 over s plus 4 square plus 3 square. What's the second one? The second one is 2 over s plus 4 square plus 3 square. This one, the first one, perfect. We don't need to do anything now. If I take the inverse Laplace to the first one, what am I going to get? I have this exactly in the same format. I'll get 2 times this, right? Yeah. But the second one here, this is 2 over this. If I need to use the Laplace table, especially over here, the numerator needs to be, instead of 2 here, this should be what? This should be the same as here. It should be omega. So the numerator here should be 3 instead of 2. So then what do we need to do? Divide it by 3, right? And you can move the 2 over here. Now this time, this term and this term, right, they're exactly in the same format as what's given in the table. So you can just literally take the inverse Laplace from the table. Okay. Move these 2 terms back into here. Don't forget a negative sign at here. So now I'm ready to get the inverse Laplace, because everything is as simple as it is now. So we get 2 times e to the power negative 3t, that's the first term, and then minus the inverse Laplace of this term, which is, let's go back here, the inverse Laplace is this term here, e to the power negative at, a is this, then cosine omega t. So e to the power negative at, negative 4t, cosine omega, omega is 3, and here is 2 over 3 e to the power negative 4t and sine 3t. Altogether times u of t. Okay, if you don't time u of t, probably won't take any mark. But just remember, we're talking about causal signal in here, right? Yeah, so times u of t. Okay, so this is an example to show you if the denominator contains complex conjugated roots, how can we manipulate this fraction into the format given in the table, either this one or this one. So then you can directly use the table to find its inverse Laplace transform. Okay. So the trick is how you can manipulate the bottom first and then manipulate the top to match the table. Right? Yes?
How did you get the 2 times s squared?
2 times s squared.
2 and then it's a bracket.
Here?
Yeah.
This original here is 2s. So I just changed the s to s plus 2. Right? It's because I need this to be s plus 2, because bottom is s plus 2. Yeah, so the 2 you can keep it there, 2 linearity, right? You can always take the 2 out when you take the inverse Laplace transform. Okay? Yeah. You need to practice, definitely you need to practice on this. Okay, you need to basically get comfortable with how you can manipulate this kind of case to get the inverse Laplace transform. Okay. That's case number 2. So let's take a look at one more case. Okay. This case is when the denominator contains repeated roots or oppose. Okay. So what do we mean by repeated? Basically means this. So I'll show you an example here. So let's say my y of s equal to 2 over s squared and then s minus 1. So if you look at the denominator, if you set the denominator to be 0, what we're going to get? We get s equal to 1 and then s equal to 0. But this s equal to 0, this is the so-called repeated, how many times? Right, 2 times. That's what we call the repeated roots. If this is the case, so how we're going to do? So let's use a cube here. Okay, that's s cubed. So this time 3 times now. Let's use a cube to look more general. So how do we do the partial fraction expansion for this one? So we do this. Okay, for the repeated part, a over s, b over s squared, and c over s cubed. So you have to write this s cubed term into 1, 2, 3 terms. Okay, from first order, second order to the third order. And then the last one is s minus 1. Okay. Okay. Now to find a, b, c, d, the comparing coefficient methods will never go wrong. Okay. Again, you compare coefficients. So you can move this everything back into single term. So this is a times s squared times s minus 1, b times s times s minus 1, and c times s minus 1, and d times s cubed. The whole numerator at here should equal to 2. Group all the similar terms and then compare coefficients. So once you group all the similar terms, for s cubed term, you have s cubed term. Here you have s cubed term. It's a plus d. For s squared term, you have negative a plus b. For the s term, you have a negative b plus c. Constant term, negative c. So basically means this is 0, this is 0, this is 0, this is what? 2, right? Compare coefficients. So finally you can get all the answers at here. So a equal to negative 2, b equal to negative 2, c equal to negative 2, and d equal to 2. Okay. Alright, so that's how you get a, b, c, d. Compare coefficients. Once we get a, b, c, d, okay, and we can start to take inverse Laplace now. So basically it's the inverse Laplace of negative 2 over s, 2 over s squared, 2 over s cubed, and 2 over s minus 1. Use the table. Let's take a look at the table here. What is the first inverse Laplace transform? Here's s term, right? So when you have a constant over s, just move it out. This is negative 2 times u of t, right? So, or negative 2 times 1. I'll move the u of t to the outside here. What is the inverse of 2 over s squared? It's over here, which is t. What is negative 2 over s cubed? So where is it? We don't have it here, right? But we do have what? This, yes, t to the power of n. So when n equal to 2, you have s cubed at here, and then you have a 2 factorial at here, okay? Yeah, but we don't need, we do have a 2 factorial at here. With 2 factorial is 2, yeah. So basically 2 over s cubed is t to the power of 2. And then the inverse of this is 2 times e to the power positive t, because this is minus 1. Right? So you go back to here, and finally times u of t. Is that good? Yeah. So that's the idea for this kind of case at here. Okay. I'm using s cubed here. You might have what? For example, s plus p to the power of 3, for example. Okay. With no difference, you just change the s to s plus p, and you can compare coefficients. You can get an answer. Okay. There is a formula, but I think at this stage I don't think I encourage you the formula. When you're using a third-year learning control system, I think you will be presented with the formula. So when you have a you do have a formula to calculate ABC when you have this kind of repeated roots. I have it in my lecture notes. You can take a look at it. Okay, but I think comparative coefficient is enough. It's not sophisticated either to get the constants value ABC. For the d value, okay, for the d at here, you do have an alternative. If you recall that when you calculate the d, you can also use a formula which is s minus 1 times y of s, and then let s equal to 1. So you can also get the d value using that formula. Okay? Yeah. Yes?
Just at the top of the when we're getting the partial fractions, is it possible to work with only 2 fractions?
Is it possible to what?
2 fractions. Does the denominator also have to be in the power 1.
You mean just these two?
No, for example, the 2 over s cubed, s minus 1. Could it be a squared plus bc plus c over s cubed plus d over s minus 1?
Oh, you mean put an s here?
Yeah.
No, you put an s here and then you cancel out the bottom here now, right? Yeah. So the idea is when you have an s cube here, the partial fraction expansion could contain first order, second order, and then third order. So that's why you have 3 terms set here. Yeah. Okay. Any question on this? Again, you will need some practice on this, okay, to get comfortable with this approach here. But the bottom line is you need to stick with the principle, right? How to do partial fraction expansion under different scenario. I do have a table edit here for your reference. So there is a small table edit here. A little bit sophisticated case, right? So if you have complex conjugate numbers, your partial fraction expansion form will be just like that. If you have a repeated roots, right? You see that you have each one of the term you have to repeat it. Each order has to be repeated. And the last one is, I don't think I'm going to test you this, but this is basically a combination of the complex conjugate plus a repeated roots, right? Yeah, that'll be very complicated to a lot of computations if this is the case. Okay. Any questions on finding inverse Laplace through partial fraction expansion? All good? All right. Okay, so let's move on in here. So I do have another topic related to Laplace, which is called the transfer function. Transfer function. Okay. We're actually going to loop back to the impulse response. Okay. So first of all, definition. Okay. Given a system like this, with input x of t and output y of t. Okay. The definition says this: the transfer function of an LTI system is defined to be the ratio of Laplace transform of a system output to the input. And it's not finished yet, and this is the last part. You have to be very careful here, assuming that all initial conditions 0. Okay, that's the definition. I need to write it down here because I know every time there's a lot of students. It's actually very simple to get the Laplace the transfer function, but somehow there are a lot of students having trouble because they don't read this definition completely. Okay, so let's read it again. Transfer function of LTI system is defined by the ratio of the Laplace transform system output to the Laplace transform of the input. And when you're calculating through the process, you have to assume that all initial conditions to be 0. Okay, so I'll show you that why. Okay, yeah. So for example, right, if this is the system at here, okay, if this is the system in here, transfer function is basically we use h of s to represent the transfer function. It's the ratio between the output Laplace over the input Laplace. It's as simple as that. You use the output Laplace divided by the input Laplace transform, and then you get the transfer function. Okay. So what do we use the transfer function? Transfer function is a very useful, very useful tool. You can replace your system with the transfer function. The transfer function literally represents the characteristics of the system. So my original system can be re-sketched as this. Instead of the t domain, right, we can represent the system using Laplace transform. It's a Laplace transfer function, and the input is x of s, output is y of s. So this is completely an S domain now, right? Yeah. Okay. So let me show you examples how to find Laplace. How do you find the transfer function? Okay. So here's an example. Okay. A system is described as, okay, using the following second order ODE. So let's say we have a system that's described by this second order ODE. X of t is input, okay, and y of t is output. I want to find the Laplace. I want to find the transfer function of this system. Okay, so what is the transfer function of the system? Okay, yeah. First of all, the input x at here, okay, it's not given. It's a general input, right? So, and that actually makes sense. I mean, when you have a system, you can practically give any kind of input to the system, right? Yeah. But if you have a specific input, you plug it over here, then you will have an expression on the right side, right? And then basically, you can actually solve that second order ODE, right? Like what we did, whatever approach that you can use. Okay? But the question here is looking for the transfer function, okay, h of s. And transfer function by definition is the ratio between these two, okay, these two. And what? Assuming all initial conditions to be 0. Okay? So here's what we do. We don't have y of s, x of s directly showing at it here. Okay? But if we take Laplace transform, okay, of both sides of the equation. Okay? If I take Laplace transform both sides of the equation in here, then I will have the y of s and x of s showing up. Right? So let's see what's going to happen if I take a Laplace transform of both sides of this equation here. Taking Laplace transform the left side first. Okay? What do we get for Laplace transform of a dy, a second order dy over a second order derivative of y over t? You use the table at here. This is the table. When you have a second order derivative, its Laplace transform is this one. Okay? Yeah. So basically we get 9 times s squared y of s, and then according to the table here, you have s y of 0 minus y prime of okay. And similarly for the second term, you get s y of s and then minus y of 0, right? So that's first order Laplace transform. And plus 13 y of s, right? And the other side is this, 2 times s times capital X of s, okay? And then plus, and now plus minus x of 0, and then plus last one 3 times x of s. Okay, that's if you apply the properties from the table, right? Laplace transform, that's directly what you get at here. Now this is where you have to be very careful now. What are we looking for? We're looking for transfer function at here. So when you're looking for transfer function, you assume all of the initial condition to be 0. So you can write this one at here, that's fine, but then for the next process, you have to get rid of all of this. Okay? Yeah. So now you get 9 times s squared, capital Y of s, plus 12s, plus 13 y of s, equal to 2 times s, capital S, x of s, and 3 times of this. Okay? So I'm showing you this step here, all these terms. But in the future, when you're taking Laplace, if your objective is to find the transfer function, you really don't have to write this here. You can just look at this. Okay, what's the Laplace of this one? 9 times s squared y of s. Okay, because you're looking for transfer function, right? Yeah. It's not like you're solving it. If you're solving it, then you definitely need to keep this one here. Okay. So from here, we take the y of s, okay, as a common term, x of s as a common term, and now you find the ratio between the output and input, which is okay, so you get this transfer function of the system here. Is that clear? Yeah? So just always remember, right? What are we looking for? Is the question asking for transfer function from a given ordinary differential equation? First step, you take Laplace transform of both sides of the equation. When you're doing this, you will knowingly set all the initial condition to be 0. Even if the question give you initial condition, the question maybe states like this: a system is described like this, y prime of 0 equal to 1, y of 0 equal to 2, for example, right? So I will purposely trick you. I give you the initial condition, but when you're looking for transfer function, what do? Right? Assume all initial condition to be 0. So you have to do that, okay? Yeah. So let me give you one more example here, okay? As a sort of a circuit example. This is a RLC circuit with inputs as V of t and output as VO of t. So let's call this VI of t. You have an RLC circuit, and the question could be, what is the transfer function for this circuit system? Okay. So first step you do is you have to come up with ordinary differential equation governing this circuit set here. You can use KVL law. Okay. So when you add up all the voltage across each component, you should end up with the same as the input. Okay. All right. And the output at here, the input is V. And the output at here is the voltage across the capacitor. So that's 1 over C I dt. Right? So that's basically, it's this term at here. Okay. So how do I get the Laplace? How do I get a transfer function? So transfer function basically means we're looking for the ratio between the output, which is VO, and VI. Right? So we're looking for this ratio at here. Okay. So I will actually get this out of these two equations. Okay. Out of the two equations. I'm going to take a Laplace transform of the first differential equation. Okay. I don't worry about it. You have a double integral. You have a one integral here, one derivative here. That's fine. Okay. That's actually also normal. So if I take Laplace transform of both sides here for the first one, when I take this, because I know I'm trying to get the transfer function, so I'm going to take it for granted that all the initial condition will be 0. Then the Laplace transform for this term is L times S, I of S, R times capital I of S. 1 over C, Laplace transform of integral is what? 1 over S, F of S. Yeah. So if you recall that, S is a derivative action. 1 over S is a integral action. And VI of S. And I also take the Laplace transform of the second equation here. So we get VO of S equal to 1 over S, 1 over S here, and I of S. So we got I of S from the top here, and then substitute into the second, then you'll get a relationship between VO and VI. Right? So at the end, you get your H of S, VO over VI, and that's 1 over LCS squared plus RCS plus 1. So that's the Laplace, that's the transfer function of that RLC circuit. Okay, good. I know you have the question here. What exactly does Laplace? What exactly does transfer function do? Right? Yeah. It has so many things. Actually, I can't even tell you. So, but there's one thing I can tell you. Actually, may not be today. Yeah. Yeah. Well, actually, we can start it here. Okay. There's one thing we can use the transfer function is the impulse response of the system. What's the definition of impulse response? That's right. And the corresponding system output is called impulse response. Okay? Yeah, very good. I think when I introduced the concept of impulse response, and I have actually spent a few minutes to emphasize the importance of impulse response, or the importance of getting impulse response. Because when you have impulse response, and then what? You can literally get any other system output, use the convolution of the current input with the impulse response. Right? That's the property of LTI system. Okay? So literally, once you get the impulse response, then you don't need to do any experiment anymore. You can mathematically just do the convolution, then you get the current system output, right? Yeah. But I did mention one thing. How do you get the impulse response, right? You can say, I'll give the system impulse signal, but impulse signal is a signal that is infinite when at the t equal to 0. So reality, in real life, you can generate an impulse response, right? You can generate an impulse, but you can't generate an impulse with infinite magnitude, right? So experimental wise, you can't just get an impulse response. But mathematically we can. Now we have the transfer function, we actually can get the impulse response now. So here's how. Okay. So when input x of t equal to delta t, right? That's the impulse signal. We get the output is impulse response. We call that h of t. Okay. So what is the Laplace transform of delta t? 1. Right? If you look at the table, Laplace transform is 1. And now I have already learned the definition of a transfer function. Okay, this is the definition of transfer function. The ratio between y and x is the transfer function. So if x of t equal to delta t, right? So now this x of s here could be anything, right? It could be any input here. But now I will let x of t to be delta t, okay? So then your x of s equal to 1, right? Equal to 1. And if xs equal to 1, then what is your y of s now? So from here, you get your y of s basically equal to h of s times x of s, right? So if your input is delta t x of s is 1, then your y of s basically equal to h of s. If I take the inverse Laplace of both sides of this equation, we get y of t equal to h of t. By definition, when your input is impulse signal, this y of t is called what? Impulse response. So basically your impulse response set here is what? The inverse Laplace transform of the transfer function. So I'll write it down in here now. So basically impulse response of the system is the inverse Laplace of transfer function. Okay? Yeah. So that's mathematically how you can get the impulse response. So if you look at the examples we have here, right? For example, right? That example. This is a differential equation representing the system. This is the transfer function. If we ask for what's the impulse response, then you just take the inverse Laplace of this one here to get the impulse response. Okay? As RLC circuit, you take the inverse response of the Laplace transform of this, then you get the impulse response. Okay. I'll show you one example in the next lecture. Okay, and please don't forget that next week and the week after we'll have 2 quiz. Okay, simple quiz, just to prepare you for the final exam. Okay.